we're going to learn a little bit about radiation and greenhouse gases, and going to define actually what is a greenhouse gas, why are they doing the things they're doing, and why are so many people worried about them. And to understand greenhouse gases, we really need to understand radiation. And so we need to understand what radiation actually is, what it looks like, and what it means for us on Earth. So this is the sun. This is the source of our heat in our atmosphere, in our oceans, and on land. And so today we're going to do a calculation, and we're going to do a radiation energy balance budget. We're going to look at the equilibrium temperature of the Earth and calculate that, and compare it to temperature at the surface. And I'll define those two terms. And then we're going to look at greenhouse gases, and the role, and we'll look at the role of different gases, what they're doing, and why. And so we'll get into some chemistry. I had some questions yesterday about radicals, I believe, because we'll get down to electron structure. We will be able to define and what a radical is. So radiation spans a really wide range of wavelengths. And so we've got the far UV, and that's below 200 nanometers. So this radiation is going to fry you. We don't want any of that. The mid UV is also going to fry you. At the surface, we definitely don't get any far UV coming down. There is minimal amount of mid UV, and then really it's the near UV above 300 nanometers that we start to get some of it at the surface. And then, of course, the visible range. So in terms of, this is all solar radiation coming in down to there. Then we get into the near infrared. So infrared is a heat. It's heat energies there. And then we get to the mid-infrared, far infrared, and then out to the microwave. And we can go further than that in terms of wavelengths. But so you're starting to get in the microwave, you're millimeter to meters. Now, around the mid-infrared, we start talking about emission. So we've got solar radiation coming in, and then we start talking about emission of the Earth going out. And what defines where something emits is the temperature of it. So that equation, and up the top here, we've got the energy of the emission is equal to some constant, and it happens to be Stefan's, by the temperature to the power of 4. So the temperature of something really defines the energy at which it's emitting. So the sun is particularly hot. So 5,800 Kelvin. And we've got this constant, we multiply that by, and we can calculate the energy being emitted by the sun. And so that's what we do. And that's this term here, called the solar flux. And so we've got a term for the energy there. Now, to work out what that means for us here on Earth, it's how much is actually going to reach us. And I'll just draw a wee diagram of that. Look at the right screen. So the sun is quite big, and we're very small sitting out here. And so what matters is the sun is going to be emitting that energy in all directions. And so that's the first thing that we really want to take away, is that emission from any object, a black body, is in all directions. And so only a very small portion is going to make it to us here on Earth. And so what matters is how wide the radius of the sun here. So the radius of the sun, and then this distance between the sun and the earth. And so that's what we've got there. And it's the ratio of those. So we've got the radius of the sun on the top, and then the distance, the interplanetary distance, together here a term to define what's called the solar constant for Earth. So this is our solar constant. And what we can do is calculate a number down here. So this is all theoretical to this point. Physics is defining this number here. It's 1,390 watts per square metre. And measured actually at the top of our atmosphere is 1,380 watts per square metre. Now, does anyone know what when we talk about the energy balance of the Earth, how much we assume is coming in from the sun? Does anyone have a feel for that number? That's okay. You're going to get that on the next slide. So what we've got here is, I'll go back to my document. Yeah. Because this is the Earth, and if I could draw a perfect circle, which I cannot. So that's the radius of the Earth here. Now, when the solar radiation is coming in, it's actually only hitting one side of the Earth at one time, as we know. I'm going to have to excuse myself just for a minute. Sorry. Terrible when your nose starts running. So what we have is the radiation's only hitting one side. So it's effectively only hitting a disk. But when we talk about emission, we're talking about a sphere. So we're comparing a disk to a sphere. So something that's rather circular, like this. And so that's the surface area of a disk. Does anyone remember? Pi r squared. And the surface area of a sphere? The total surface area of the Earth is actually, it's 4 pi r squared. So you've got the volume. The volume's 4 over 3 pi r cubed. But the surface area is actually given by 4 pi r squared. And so that's the difference. So you're getting all that radiation coming in on one side, but you want to have it expressed over the entire globe. And so that's how we come up with the magic number of 345 watts per square metre. Yeah. And that helps us. So, and actually it's 342 as we have that as our incoming solar radiation. So this plot may be familiar to many people. It's from the IPCC, and it's the energy balance of the Earth. So this is our source term. This is the solar radiation coming in. And some of that gets reflected straight back out. So that's the reflected solar radiation, about a third. And so our albedo of our Earth is about 0.3. So how reflective is the Earth? And how much is going to come through that? And so when it does come through and it's not been reflected by aerosols and clouds, which is something that we're going to get to tomorrow, it's coming down and it's being absorbed by the surface of the Earth. And we heard from Pete that a large proportion of that is going into the oceans. A little bit's reflected back out here from the surface itself. Some of it's absorbed by our atmosphere of that incoming and solar radiation, and that is in the UV wavelengths. So this here is what ozone's doing there. But this part of the energy balance here is then, once the Earth has that energy, it wants to re-emit it, and it will re-emit it at its own temperature. And so we can calculate what that temperature is, because we know many of the terms now. So we can balance that incoming and outgoing. So we've got a term here. So our energy coming in is that solar constant, unless what is reflected back out to Earth, so we get 0.7, we take an albedo of 0.3. So 0.7 is reaching the surface of that solar constant, and here we've got that coming in and just hitting the sphere. So that pi r term is just, we're hitting sphere. But when we emit, and we're sending it back out, we emit over the entire surface of the Earth. Yeah, so we're doing that there. And we've got this energy there. Now that emission term of the Earth, the energy at which the Earth is emitting, is temperature dependent. And we've got this Stefan-Boltzmann constant. And so what we do is we make the incoming term equal to the outgoing term, so equate those to each other, and then we substitute in what that emission term is here, the energy, and we come up with this magic term where we can calculate what the temperature of the Earth is, so what it's emitting at. When you're out at space, what does the temperature of the Earth look like? So I want everyone to just put in the numbers and tell me what the temperature of the Earth is if you're sitting out at space. Do we have an answer? $255? And in Celsius, for people who don't like Kelvin? Minus 33. Oh, no. Yeah, minus 17, yep. Yeah. So we have a temperature of the Earth that is 255 Kelvin. And it's pretty cold. So why is the surface of the Earth not cold? The greenhouse effect. So the greenhouse effect. So we see that we've got, so yes, it's minus 17 will be what the temperature would be, and we're actually at 15. So there's a 33-degree difference between those two. And we've got clouds and greenhouse gases, we have an atmosphere which is causing that, because things are not escaping directly back out to space. And it's this massive term here called back radiation which is causing that. So that's the greenhouse effect. And what we can do is look at different planets, actually. So we have here, this is Earth. So this is our solar constant. So that's really, it's a function of how far away we are from the sun. And we can see that Venus is a little closer and Mars is a bit further away. And then we can look at the equilibrium temperatures that these planets have from space. So Venus a bit cooler, and Mars again much cooler. This is what they look like from space. What we have here is the temperature actually at the surface of those planets. So 288 as the equilibrium, the surface temperature of the Earth, so that's 15 degrees. And you can see this massive amount of difference between what the surface temperature of Venus is. So that's 735 Kelvin. That's really hot. And then we've got Mars, which is only marginally different from its equilibrium temperature. And we can start to look at what their atmospheres look like. So we've got CO2 in the atmosphere here, very small percentage, and actually wrong, right? It should be about 0.04 now. And but Venus has a runaway greenhouse effect, and that really accounts for that massive difference there. But when you look at Mars, the CO2 is about the same. And so why isn't it having such a large effect on that? One factor is that it's further away, so the solar constant is pretty small coming in. So it doesn't have the same amount of energy that can be trapped by that. And then you have to look at the other constituents in the atmosphere, because CO2 obviously is not explaining all that difference in that. Can anyone tell me what the strongest greenhouse gas for Earth is? Water? Yeah, it's water. And why don't we worry about water? It is short-lived. What controls the amount of water in the atmosphere? What does control it? Temperature. Temperature controls the amount of water in the atmosphere. So how much water the atmosphere can hold is controlled by temperature. Otherwise, it precipitates out. Well, temperature controls the precipitation. So we can have a look at CO2, and people are probably fairly familiar with this plot. This is Cape. We've got the Cape Grim flasks and in situ up here in the purple, and then in this lightish green colour we have Lordone iceberg. So going back 1,000 years, you can see there were very little changes, and then the start of the Industrial Revolution, and these really large increases in CO2. Now CO2 is a relatively boring molecule because it just, apart from in the oceans, it does some chemistry, but in the atmosphere it does very little. It just sits there and accumulates. And that's the problem. So these are the messages from the IPCC about the warming of the climate system being unequivocal. And there are changes now, observed changes that are unprecedented over decades to millennia. So the atmosphere and ocean have warmed, and the amounts of snow and ice have diminished, sea level has risen, and the concentrations of greenhouse gases have increased. So the science behind what is driving these changes is well established now. So back to our radiation, and back to absorption and emission. Now this is quite a nice, it's a schematic, but if you can imagine that this is wavelengths along the bottom. This is our solar input, and this is our, and this here is our optical windows. So we get, this is the solar influx here, and this is where we get to see some things, and then you're getting an output, and this is where the radio wavelengths function now. Now if we look at just black body radiation, we've got around 6,000 Kelvin. This is what the sun looks like. And this is what Earth looks like at 255 Kelvin here. So this is our input, and this is the way of cooling the Earth here. Now all down here what we have, this is ground level absorption, and this here is up at 11 kilometers. You can see that the troposphere has a fair amount to answer for, and many of these bands here are related to water. But there's also an awful lot of other things going on. What you can notice here in this UV range, this is all UV, and so we're always progressing across here. Got the wavelengths up the top there. So up to 300 nanometers here, water and oxygen are absorbing almost completely. So we're getting nothing coming through there. So almost, this is percentage of absorption. So when the atmosphere absorbs it at 100%, nothing's coming through. And then a lot of visible light comes through, thankfully. That's why our eyes are developed in this wavelength range. And then we've again got oxygen, ozone, water. Water, all these big bands repeating here. We've got CO2. Here are those little bands there. Out here again. Now what the special thing about CO2 is, and it's much clearer to see them down here where we get rid of the water. So the difference between this one here and this one here is essentially water. You see these CO2 bands. They start occurring in regions where the Earth is re-emitting out to space. And so they have a larger impact there. And then so, again, look at water out here in the microwave region. Does anyone know how your microwave at home works? It does. It does. And we'll get into that later, but it actually causes the water molecules to rotate. And so that's that water rotation. And so they're moving around, converts their rotational energy into kinetic energy. So it heats up your food. And so it's in this little window here, 8 to 13 microns generally is where the Earth is managing to effectively cool itself, because you can see that water is blocking many of those other areas. And this is just another, this is the incoming, this is the solar curve with all the absorptions in there. So you can see that the atmosphere will absorb the solar radiation coming in as well as what's going out. And so that's why it becomes reasonably complicated about the temperature response of the atmosphere to increased levels of carbon dioxide, because there are other things that are going on and other absorbers in different regions that start to play into that significantly. So water is the most effective greenhouse gas, but that's controlled by temperature. And we don't worry about that too much, except for the water feedback. So an increase in temperature will allow the atmosphere to hold more water. So it's a positive feedback. You're going to get, because you've got more water in the atmosphere, you're going to get more heating. Positive there. And then we've got these other terms. So CO2, methane, N2O, ozone, and the CFCs. Now, absorption is an extremely nonlinear process, and this slide begins to touch on that a bit, because we try to quantify what is doing how much, and you do that by removing them and leaving them in there, etc. So what's the percentage of trapped radiation remaining? If you remove all, you've got nothing remaining. So no atmosphere, you've got no radiation being trapped. If you don't remove anything, you've got 100%, so it's just normalized that. Now let's take out water, ozone, and clouds. So 36% of the radiation remains. Okay, so they're doing quite a lot. Water by itself, we just take that out, and so you're getting 64 of the radiation being trapped. So water is obviously extremely significant. Okay, let's just take out, it's obviously less, it needs to be combined with clouds, and it's hard to take out the water and not the clouds, right? So these are obviously idealized runs. Now clouds are less effective, so they're only trapping about 14% there. Ozone is only really 3% of what's coming in, but it's doing it in different wavelengths, etc. So and CO2 by itself, it's significant, but it's really those combinations that can start to account for the radiation that is remaining in our atmosphere. So what is absorption? What does it mean? So now we start to get into some chemistry. How do molecules interact with the radiation? That's what absorption is. And then a more basic question, what actually is a molecule? So we'll come to that. And then actually, what is an atom? And why don't we see atomic absorptions? Why don't they play into our greenhouse effect? So we're going to have a look at a carbon atom here. So an atom has a nucleus, and then we have these electrons spinning around in what are called orbitals. And so this inner orbital has 2 electrons. Now electrons like to be in pairs, and when they're not in a pair, it's called a radical. So we've got 2 in the middle, and then we have each, like an outer shell of orbitals would be perfect if it has 8. Now carbon has 6 there, so it's got space for 2 in this outer shell of spinning electrons. So it's got 6 in total, 4 in this inner orbital there. So there's our protons in the nucleus there. So we've got protons and neutrons in the nucleus. That's the weight of our atom, and then we've got all these electrons spinning around that, and they create the volume, and you can calculate the distance of bonds and things, because these electrons, they want to be far away, but they're also attracted and in orbitals around these atoms. So we've got our inner orbital and then our outer orbital sets there. Now, each of those, as you're going out, has increasing energy, and they're discrete. So if an electron jumps from one orbital to the next, it's a discrete amount of energy, and so that's where the spectra comes from. And so what happens is you can excite so you've got this n orbital, jumps up to this one. As it comes back down, it emits an energy of a certain frequency. So that's Planck's constant and a certain frequency. That's the energy. So coming back down is where you do the emission. The absorption is just putting it up from one level to the next. And there's a few different types of absorption. Now we can have a look at the periodic table here. These guys are the happy ones. So the noble gases. Because they've got full electron shells. So 2, and then we've got 2 in that inner shell, and then 8 in subsequent shells. So we get 2 plus 8 is 10, plus 8 is 18. And then once we get down here, we've got all sorts of other fun orbitals, which I won't even get into. And so you get a few more. But these ones here, they're perfect. So they don't need to react with anything. It's why they exist as atoms. Now, everything else that's not is one short, need to cooperate. They want to grab something from someone else. And so that's why everything over here is all reactive. These guys here are one electron short of a full cohort. And so they're extremely reactive. And these here have got 1 too many, so they like to give it away. And so on. Now, carbon's a bit different, you see. It's got 4. So it's about in the middle of the road. So it can go either way, but really likes to bond with itself. So silicon has a similar property. These guys here like to form the anions. These guys here like to form the cations. And so molecules, that's how you get molecules happening. They don't have the full collection of electrons, and so they need to go and cooperate. So nitrogen has an atomic number of 7. It's 2 short. So it has 2 in the inner and 5 on the outer. It wants to have 8, so it needs to go and get an extra 3, which is why nitrogen will form a triple bond. You can draw that up if you like. So you may remember your dot structures. So you just draw the outer orbitals, and I'm going to draw these five electrons and you'll see why I put them like that. So each of them have 5 electrons, and they want to be in electron pairs. So we've got one pair there on each, and then we pair them up. So now if you count how many this nitrogen has, it's got 1, 2, 3, 4, 5, 6, 7, 8. So it's happy, it's got 8. And this one also has 8 now. And that's why nitrogen has a triple bond. So I've just drawn that dot structure. Now we can do that for all sorts of things and things that are much more complicated than nitrogen. And that defines what their structure looks like. Now, so I've done it for nitrogen. CO2, it's a linear molecule. And water is actually bent. And so I won't draw them up. But that's key to understanding why 80% of our atmosphere is nitrogen, and yet we don't talk about it as a greenhouse gas, because it does not absorb in the infrared. And I will talk about why that is. So we've got energy transitions. Now they can be, this is the length of separation within a molecule. So as you stretch a bond, eventually you'll break it, and that's dissociation. So down here. And what we have is these vibrations. So the molecule can do this. But it does it at discrete energies. So when you give it lots of energy coming in, it'll vibrate like that. And what it can do is actually the electron can jump up to a completely different state. So that when the electron jumps, that can be a very energetic, and it is very energetic. And often enough, you can see that that energy is enough to break that bond over here. So it jumps up and generally blows the molecule apart. So that's called an electronic transition. And that happens in the UV. The vibrational transitions happen in the infrared or the Raman. Now, there are some rules. So electronic everything does this, and that's really driving how ozone absorbs. It absorbs the energy, blows the molecule apart. So you don't. That's why the reactions in the stratosphere are called photodissociation. So it's absorbed and then blows apart. And that's what happens to CFCs, N2O, breakdown in the UV. Now, vibrational transitions, and this is what is important for greenhouse gases, this is the infrared absorptions, they have some rules. So the molecules will vibrate, that's fine. So they stretch, or they can bend, or they can have asymmetric stretches. All of these things, they require less energy, and they're only active in the infrared if the dipole of the molecule changes. So nitrogen is a diatom, it's symmetric. And so there is no dipole on this molecule. And if you stretch that molecule, it still has no dipole. And so that's why oxygen and nitrogen have no infrared absorptions from vibrational transitions. CO2 is also a symmetric molecule. It's linear, and its symmetric stretches don't absorb in the infrared. But it can do this, and it can do that. And so those are active vibrations which absorb the infrared energy, and why CO2 is considered a greenhouse gas. And all other molecules in some way can induce a change in that dipole usually, unless it's extremely symmetric, like nitrogen and oxygen. So most molecules will have an absorption due to this vibration. Now, only molecules that have a permanent dipole will absorb in the, will be able to have a rotational transition. And so water, which is a bent molecule, which means you have an oxygen at the top, which is negatively charged, and you have hydrogen at the bottom, which is positively charged, and so you've got a dipole. And so when it rotates, it has a changing dipole, and so water has both the vibrational and the rotational. So you need to have a dipole to have rotational spectra, which is why water works in the microwave. If you tried putting in an ammonia cation, that would also rotate in the microwave. CO2, which doesn't have a dipole when it's just in its normal state, because CO2 being, I'll come back across. And so we've got CO2. So this is going to be slightly negative, and this will be slightly positive, and this is slightly negative. It's balanced overall. There's no dipole. Whereas water, which is like this, you've got this slightly negative and this slightly positive, and so it's all the time got a dipole. So there are little dipoles within the CO2, of course, so you've got a slight positive there, a slight negative there, but overall it's zero there. So this will not have the selection rules to be active in the microwave region, but water for sure does. It has a permanent dipole. You just need to induce a dipole for it to be active in the infrared. And so CO2 is actually it's an interesting molecule because it needs to break some rules to be able to be active sometimes. But like with an asymmetric stretch, it satisfies that rule straight away. so upset. So I've gone through that. So we're done with rotation. So now we can start to explain these things. So now we know why the absorption and readmission of radiation of molecules results in increased surface temperatures. And we'd be in big trouble if nitrogen was a greenhouse gas. So making up 80%, but it is not considered a greenhouse gas. Ozone's also a bent molecule, has a permanent dipole. It absorbs UV light by those electronic transitions, so generally it blows apart. And why does that result in the local heating effect there? It's because you've absorbed that solar radiation, it blows the molecule apart, and that results in changing the UV energy into kinetic energy. And that's what happens in the reaction. Now, the very first person to identify that carbon dioxide had an infrared absorption was John Tyndall in 1859. And he showed that carbonic acid, which is now known as carbon dioxide, ozone and things, they have this absorption in the infrared. And so by putting more of them in the cell, he worked out that you can stop the transmission of heat. But he did note that oxygen, nitrogen, and hydrogen were transparent to radiant heat, while other gases were quite opaque. So he was the first to identify this effect. Now, let's leave this in work. See how we go. It might not work. All right. The drivers on my computer don't work for that. It's not a very exciting one. It holds the candle up. It stops eventually you stop seeing the heat of the candle on the infrared camera. So I'll let you look at that in your own time. Why does the stratosphere cool with increased greenhouse gases? Something you may all wondered about. Now we know that the Earth will not change that temperature from outside. So we know that the Earth from in space will look like 255 Kelvin. So we can do whatever we like with our atmosphere and it will still look like 255 outside, basically. It's only us at the surface or in different parts of our atmosphere that are going to care about that. And so what we're actually doing is raising the point in the atmosphere, so raising the altitude of where the mean temperature at 255 Kelvin is going to be located. We're going to bump up the height of the tropopause. And at some point, so this is our control run there, and we're bumping up the profile, the temperature profile, increasing that height of the tropopause, and at some point it just crosses over. And so we're getting a cooling of the stratosphere up here, and we're getting an increase at the surface. So that's effectively what we are doing to our atmosphere by putting more CO2 and greenhouse gases in there. It's different at different wavelengths, and so this is just an example, but it's a nice way to start to understand how the atmosphere is going to respond to temperature, to perturbations and its constituents. So we've dealt with our absorption now, so this is a bit of a summary. we've got electronic transitions. They're happening in the UV and the visible. That when you think of that, you've got UV visible, that's solar radiation. When we've got vibrational transitions, that's happening in the near infrared, and so that's radiant heat. That's emission of the Earth. We can see that there. And then we've got rotational out in the microwave, and we don't worry about that too much. We can use it. So infrared and microwave wavelengths are obviously not limited day and night. So for measurement techniques, if you want something that you can measure at all times with, you need to be looking for absorptions, so satellite absorptions, etc., that work in the infrared or in the microwave. And it's much easier. You need the UV and the visible to start looking at some of the radical species and to look for oxygen, etc. So now these are our selection rules, and I'll just skip that is actually my last slide. So we're done a little early. Was it clear for everyone? Is there some questions? Sure. So you need to have a dipole change for it to be active in the infrared. Yeah. So a molecule can have no dipole at the start, for example, like CO2, but as long as it can create one, it will be active in the infrared. And it does that by, so it's a three atom, my head, my arms. Doing that, I've got a dipole now. So that stretch has a dipole. By doing that, which it can do as well, got a dipole again. So there's a few of and you can calculate the frequencies of all those different stretches. But there are some, this one here, where it's symmetric all the time, is not active in the infrared. Yeah, cool.
These vibrational modes, they're very continuous spectral, or are they discrete like the atomic?
All these are discrete because they're if I go back to, where is my, so what we have is, this here is a vibrational transition. And so it is discrete in energy. Like, so there's two quanta, 3 quanta, etc. And so these are called overtones when you jump up more than one. And it emits coming back down. So you can, what generally happens is you get vibrational spectra around, because as soon as you create a big movement, actually the molecule starts having these vibrational transitions as well. And so you get something that looks a little bit like you have there and there. So, or actually it's a number of discrete lines, actually. Which is, this here whole thing is the vibrational transition, and these are the little rotational noise on top of the vibration. And so once those get smoothed out, and generally you notice that in the CO2, like it's just one big smooth peak, and that's a matter of resolution. Yeah. Cool. Sure, I'll try. So what we've got happening, just put it up on both screens. So the temperature of the Earth is 255 outside regardless. Now what happens is if you just increase that altitude, that happens out. And so you effectively, what that does is look like a warming right through the troposphere, bumped up the tropopaure's height. And because you're just bumping up the entire profile, and you've got an increase in temperature that crosses over, and you've got a cooling effect up in the stratosphere. It doesn't effectively, because the CO2 is of course density related. So whereas ozone and the temperature part is much more tied together in a layer with UV considerations. Yeah. Different wavelengths do different things. I've got another plot, I'll try and find it, which shows how this effect is at different wavelengths.